Generative Adversarial Networks, or GANs, are a type of machine learning model where two neural networks compete against each other. One generates data, and the other evaluates it. This competition leads to the creation of highly realistic data, like images or music, that are barely distinguishable from real data. The question of whether GANs can truly be creative is exciting because they learn from existing data while still creating novel combinations that appear original. GANs are fascinating because they can create things like realistic faces or artworks that look so real they can trick people. One example is a GAN that generates images of non-existent people that look like real photos. This ability makes GANs an exciting tool in artificial intelligence because they create new things and spark our imagination. The fundamental concept behind GANs is adversarial training, where a generator and a discriminator act like opponents in a game. The generator tries to create fake data while the discriminator decides whether this data is real or fake. Through this constant contest, both learn to improve until the results seem remarkably real. GANs were invented in 2014 by Ian Goodfellow, a young researcher who had a brilliant idea. During conversation at a bar, he thought about how two networks could deliver better results through competition. This crazy idea of adversarial training laid the foundation for a revolution in machine learning. GANs are transforming artificial intelligence because they can generate realistic data that was previously impossible, opening up new avenues for research and technology. They help expand data volumes by creating artificial X-rays for medicine, for example. Their ability to produce synthetic data makes them indispensable for innovation in many areas. In everyday life, we encounter GANs in video games, where they create realistic landscapes or characters, but also in art, such as paintings that look like they were done by masters. They are behind deepfakes, videos that convincingly imitate real people, which is both impressive and debatable. Even in science, GANs are used to simulate data when real samples are missing. Under the hood, GANs work with two networks trained together. The generator creates data from random noise. The discriminator checks their authenticity. Both use backpropagation, a method for correcting errors, and gradient descent to optimize their capabilities. This creates a smart system that delivers increasingly realistic results step by step. GANs consist of two central components: a generator network that shapes noise into data, like images, and a discriminator network that evaluates them. The generator is often a deconvolutional network that builds structures, while the discriminator is a convolutional network that analyzes details. Together, they form a loop where they challenge and improve each other. The generator's task is to produce data that appears so real it can fool the discriminator. It learns to create convincing images or sounds from random values, like a dice roll, that amaze us. Its trick is to mimic patterns from real data until they are barely recognizable as fakes. The discriminator determines whether data is real or generated by the generator by examining it closely. It is trained with real and fake examples to recognize differences and outputs a probability of how real something is. The better the generator gets, the harder it is for the discriminator to find the truth. GANs learn through an adversarial game between two networks, the generator and the discriminator. The generator creates fake data, like images, while the discriminator checks if these are real or fake. With each training step, both become smarter because they challenge each other, like an artist learning to make better fakes and a detective exposing them. In the adversarial game, the generator tries to trick the discriminator by producing ever more realistic data. The discriminator fights back by improving its ability to separate real from fake data. This contest is like an endless dance where each step forces the other to adapt and improve. The loss functions are the rules that decide how well the generator and discriminator perform. For the discriminator, the loss is high if it classifies real images as fake or fake as real, and low if it is correct. For the generator, the loss is low if it fools the discriminator, motivating it to produce even more convincing data. In a training step of GANs, the discriminator first practices with real data, like photos, and fake data from the generator. Then the generator shows new fakes, and the discriminator tries to recognize them. Finally, the generator adjusts its work to better outsmart the discriminator next time. Training GANs faces issues like instability and mode collapse that can disrupt the process. Instability means that the generator and discriminator do not learn in sync, making training chaotic. Mode collapse occurs when the generator produces only boring, repetitive things instead of diverse results. GANs become unstable in training when the discriminator becomes too strong, leaving the generator with no chance. It can also happen in reverse, when the generator becomes too good and the discriminator learns nothing. It's like in a team game where one player outpaces all the others, stopping progress for everyone. During mode collapse, the generator gets stuck on a few simple outputs instead of being creative. For example, it might only draw one breed of dog when depicting dog images instead of many different ones. This happens because it finds a trick that deceives the discriminator and then stops looking for new ideas. There are exciting GAN variants that solve these problems and make GANs even cooler. GANs use special networks to produce sharp images, while WANs make training more stable. These variants show how flexible GANs are and how they can be improved for different tasks. GANs create sharper images by using convolutional networks for the generator and discriminator, which handle images well. The generator builds clear images from random noise step by step, like a painter adding details. This results in more realistic outcomes, such as detailed faces instead of blurry blobs. WANs stabilize training with Wasserstein distance, which better measures how similar fake and real data are. Unlike normal GANs, learning remains steady because this method avoids sudden jumps. It's like finely tuning a scale so generator and discriminator stay in sync. A cycle GAN is a clever computer model that transforms images like horses into zebras without needing pairs of original images. It works with a cyclical loss that ensures a horse looks the same after being turned into a zebra and back. Imagine it like a magician who only adds stripes but keeps the animal the same. This raises the question of what creativity means for machines, said to be the ability to make new and surprising things. Unlike humans, who draw from feelings and experiences, machines use algorithms and data to create something. It's like they build new figures from a huge construction kit that they've never seen before. But what is creativity, anyway? We understand it as the ability to create original and valuable ideas, often by recombining different things. Think of a chef who conjures a completely new dish from familiar ingredients. That's how something unique is created. In comparison, human creativity is special because we can connect emotions, experiences, and imagination. We create art or music that reflects our personality and deeply touches others. Imagine how a song arises from a happy moment. That's our creative magic. Now we ask ourselves, can machines really be as creative as we are? They can create new images or melodies, but they lack the consciousness and emotional depth that defines us. They're like skilled apprentice magicians showing great tricks, but without the heart behind them. Therefore, we need to test how creative a machine is. This is called creativity assessment. We often let humans decide if the result is new and exciting or use special tests. It's like starting a competition and seeing if the machine can convince the jury. More specifically, we decide with our human judgment whether AI art impresses us by looking for originality and beauty. If a machine-painted picture amazes us, it feels like a successful magic trick. We compare it to human art and check if it moves us. There are also creativity measures that try to quantify the creativity of machines, for example, how different or new the results are. One could measure how far a picture deviates from known patterns, almost like a school grade for creativity. These numbers help us understand the machine's abilities objectively. Let's get to the GANs themselves. Are they truly creative artists? They can generate new images or music by smartly mixing learned patterns, similar to a DJ creating a new song. However, they need training data as a base to conjure their art. Finally, we ask, do GANs actually create originality, or do they just copy? They transform random vectors from a latent space into unique images, but these are based on patterns they already know. It's like inventing new recipes from a cookbook new, but not completely out of nowhere. GANs, also known as Generative Adversarial Networks, are computer programs that create new things by learning from training data. They consist of two parts: a generator that makes content like images, and a discriminator that checks if they look real, much like a teacher correcting work. Their dependence on data is shown by the fact that a GAN exposed only to images of cats can't paint cars. But can GANs invent something completely unexpected, which isn't in their data? They mix known things like colors or shapes in new ways, akin to a cook who combines known ingredients but doesn't invent a new fruit. Therefore, their innovations are more like clever remixes than entirely new ideas. Nonetheless, GANs have already provided many creative examples that leave us stunned. They've created paintings, music, furniture designs, and even short text that captivate people. These works show how versatile GANs can be in various creative fields. In the world of artworks, GANs paint pictures by emulating styles like Van Gogh or inventing new looks. The generator learns what brushstrokes or colors look like and creates images that can appear lifelike. Often these works are so convincing that people think a human made them. In music too, GANs try to compose melodies by learning note patterns from songs. They can create a pleasant piano melody or a pop song, but they don't feel like humans, which makes the music less touching. Nonetheless, it's exciting how they rearrange sounds. In design, GANs help by suggesting ideas for chairs, clothes, or houses based on designs they have seen. Designers use these suggestions as a starting point and improve them, almost like a brainstorming partner. This way, GANs become a tool that fosters inspiration. GANs even write text by learning words and sentences from books or articles. They can produce a short story or a poem that sometimes sounds remarkable, but doesn't always make sense. It's as if they roll the dice with sentences and hope something exciting comes out. Yet, there are strong arguments about whether GANs are truly creative or if they just deceive us. Some say they're creative because they produce new things, while others believe they only copy cleverly without understanding. This discussion shows that creativity is hard to define. On the pro side, one might argue that GANs are like artists because they create works that surprise and delight us. They don't need instructions from people and still deliver original results. This makes them creative assistants to many. On the against side, people doubt the creativity of GANs because they lack emotions or intentions. They see GANs as smart machines that only work according to rules, without understanding the meaning of their creations. For them, true art remains something only humans can create. Generative Adversarial Networks, or GANs, are programs that show their creative power in areas like image generation and style transfer. They can generate realistic faces or transform photos into artworks, which makes them exciting for artists and tech enthusiasts. Their ability to create new content from data fascinates and invites more learning about their technique. In image generation, GANs operate with two parts. The generator paints new images while the discriminator decides if they look real. The generator starts with random points from a latent space, a kind of idea collection, and shapes them into faces as real-looking as photos. With convolutional neural networks, it adds details like eyes or hair until the result is convincingly authentic. In style transfer, GANs take a photo and give it the style of a painting, such as the swirling colors of Van Gogh's Starry Night. They separate the content, what's in the picture, from the style, how it looks, and recombine them. This turns a simple cityscape into a colorful artwork that looks like it came directly from a master's hand. In exciting projects, GANs show how creative they can be, such as inventing fantasy creatures or fashion designs. A project called Deep Dream used them to create surreal images with psychedelic patterns and many eyes, which appear dreamlike. Such ideas prove that GANs are not only useful, but can also push the boundaries of imagination.